Hi everyone. Okay, so we received Smarting from Membrane Train Smartingmobi EEG cap, and that has 24 electrodes. They are passive, which means that they don't have the amplifier on each electrode, which usually is it's usually useful because it can amplify the signal at the source before it gets noisy from the cables. But passive electrodes are quite good as well because we can filter out all the noise afterwards. It has ground and reference, so these two are one of the most important electrodes. Here we have the Smartingmobi amplifier this is the amplifier that we plug to the electrodes here, and we can easily put it in this little compartment here so that it can be portable. It sends data via Bluetooth, so this dongle is useful if we want to plug it onto our PC. And basically this dongle receives Bluetooth information coming from the amplifier. Here we have a lot of drivers that we can install, and their Smarting application that we will see in a few minutes. And yeah, this is to charge the Smarting the Smarting amplifier. So you have a really nice manual here on how to put the electrodes all together, what to do. There's also OpenViBE, but an old version of OpenViBE installed in here. So yeah, let's try it on. I forgot to say that these electrodes are wet electrodes, so we need to put gel, conductive gel here with a syringe. So for example, this is a type of syringe that we use to put gel here for each electrode, and it increases the conductivity, and it's basically just salt actually. So yeah, it's nothing toxic or anything, and it can be very easily washed afterwards. So as I said, the information, the data from the EEG, from the electrodes are being passed or amplified with this amplifier and streamed via Bluetooth to this dongle. Now, the closer the amplifier to the dongle is, the better, the less you will lose packets. And what is said in the manual is that Bluetooth range is 7 to 25 meters, and the version is 2.1, which is okay. I mean, their newer device has Bluetooth 5, version 5, so this is an older version. The resolution is 24 bits. Frequency, you can choose between 250 and 500 hertz. There's a lot of, cool information here, written down here. And they also provide a tool to assure that the, Bluetooth connection is working. However, from my experience, I wouldn't really advise you to install Blue Soleil if you know, maybe if just really you tried everything and Bluetooth still doesn't work, then maybe you can install it, because once you install it, it's almost impossible to uninstall it, and it just feels like a really unstable, unreliable tool to work with. If I would suggest you pair your device in an old-fashioned way, go by add a Bluetooth device, and well, I have already paired it here, but let me just show you the process. So you basically just go add Bluetooth or any other device. Here you click on Bluetooth, and you can, yeah, so your device should find Smarting here. If nothing works, then you should consider, yeah, maybe installing the Blue Soleil tool, but yeah, it really seems unstable. So try maybe another way. So yeah, here we paired it. Great. Now, what they provide as well, and they provide an application, a tool to stream your data. So it's called Smarting Streamer. We can connect with it. To find out where did you plug in your dongle for the Bluetooth that I showed earlier, you should go to Device Manager and check out the ports here. So I think it's either COM8 or COM9. Okay, so let's try either one or the other. Let's see. Connect. Okay, so it's connected, and now we can start streaming signals. Okay, and because we didn't put any gel, it has quite bad impedance. So impedance is basically something like a resistance, so it should be as minimal as possible, the resistance between your, you know, the EEG and your head. So when you put the gel, the impedance will reduce considerably. It will be smaller. Okay, so now we can show the signals. We can look at the signals, and you can actually also record data here. So you can record and in an XDF file, so it's quite useful. Their application is cool. Okay, so I typically use OpenViBE. OpenViBE is a tool, a visual programming tool that enables you to, you know, process the data and visualize the data and do a lot of, you know, processing and machine learning in real time. And also, you know, this is basically everything that you need to make a basic BCI work. So here in this, when you click on this arrow, you can find different drivers that are already installed here, and we can find Inbrain Train Smarting. That is what you need to click on. So here you have driver properties, and you can choose the port number. So you need to choose the one as we did earlier. I think it was COM7. So you need to put the number that, you know, your USB dongle is in. Again, sampling frequency usually is 500, but if we use 500 sampling frequency, the data might seem unstable because we can lose a lot of packets. So it's better to, you know, reduce the sampling frequency and to be sure that we can capture all the data, that we will lose less, right? So what happens usually is here you can see the device drift. And basically what this means is that it expects, OpenViBE expects to receive 250 samples, you know, per second, okay? So 250 hertz. And if it receives less samples than that,
it will show you a drift like it's losing packets, it's losing data. And so after a while, this data that is lost, it's basically, it accumulates the lost data. And then if it accumulates too much for a long time, for example, if you're recording for 1 hour, if it accumulates, then basically it will reach, this peak. It will completely fill this bar. So what happens is, you see here it's written tolerance. It's set to 100 milliseconds. So basically it means that until we reach 100 milliseconds of lost packets, it doesn't do anything. But if we here force a drift correction here, if it's forced, it means that once it gets to 100 milliseconds of lost or delayed, well, lost packets, lost samples, it will correct the drift, meaning that it will start over, start from zero. And it means that, and all of these lost packets will actually be replaced by OpenViBE will basically duplicate the data the samples that it received before to fill in the gaps. What also happens often is that the drift can go left and right, and when it goes to the right, then it means that some data it's receiving more than, in our case, 250 samples per second. So it's kind of some packets that were lost before, so it they are arriving later on. When we talk about, again, preferences, we can change this drift tolerance. You see this number. So how long would we wait before it will correct the data? And basically, if we put the tolerance, usually, if we put the tolerance too small, like 2 milliseconds, then it will correct, wait, 2 milliseconds, then it will correct the data too often, which can create a lot of artifacts in our signal. So this is not a really good idea because, well, you will often lose 2 milliseconds. It happens even with the best devices. So 2 milliseconds, if it always corrects so often, so you will get like some weird uh, um, signals, weird yeah, artifacts. So basically this number is something that you choose empirically. You see, how much you are losing packets per second and so on, so that you basically adjust this. Sometimes, I use 20 or 30, it depends. So this is something that you choose and you see, um, depending on your device. Um, Yeah, and actually here, this the sample count per cent block. This means this is something, it's not directly related to, the Bluetooth packets that we're receiving. Actually, what happens is this, when the server acquisition server, it sends data to the OpenViBE Designer, and if, in the OpenViBE Designer, uh, we will have, we will receive a buffer, like a chunk of data at once. So if, with EEG, it's most common to use something like 32 sample counts per, or buffer has 32 samples before it sends it to the designer. It fills in, and then, so what you can actually often see is in your display, in your signal display, you can see the data being refreshed. And if it's, too, well, if it's not EEG that is sent like 250 uh, in 250 hertz, but something that's a lot slower, if you wait if you have such a long delay, then you will see in your signal display it being, refreshed so slowly, and you will notice the difference. So basically, you will reduce this number if you're receiving um, these samples, if the sampling frequency is a lot lower. But this is quite okay, like 32 is reasonable for EEG. And yeah, your connection port is typically 1024, so you shouldn't change this. Okay, and what is also another thing, we can actually connect, um, we can receive data coming from an LSL, a stream, lab streaming layer. This can be very useful if you're streaming your data via LSL from another computer. It just needs to be on the same network as the one sending the LSL, and basically you can just the OpenViBE notices here it writes the signal stream, and then you just apply it. What it is also useful to look at is this generic oscillator, and it basically represents a summation of some basic, sinusoids of different frequencies. And it can be useful, to play with OpenViBE and to test your to learn actually how to use different boxes. So here we're in this, it's called the OpenViBE Designer. And what you need in your OpenViBE Designer is, first of all, the acquisition client. So basically, the acquisition client represents something that, you receive your data coming from the server. Okay, so in this case, my server, acquisition server, is on the same machine, my own computer. But if the acquisition server is on another computer receiving EEG data, and I am on another computer, then my acquisition client, I would need to change the IP address here. And I would need here to put, instead of my own IP address, I would need to put the IP address of this other computer on which the acquisition server is on, from which, okay. Then you can use a signal display box, signal display, display. Yeah, it basically permits you to display the data in real time. And this pink, basically uh, you know, you just connect the boxes, and you connect it by color. So basically, the pink one is signal stream, and you can change the name, rename the box as I renamed it here. It's called raw. And yeah, you can display raw data, for example, whatever you receive, you can see that. Okay, our raw data here is, let's see it. So, okay, because I have a lot of displays, I'm displaying a lot of things so that I will show you. So yeah, the raw signals look like this, basically. So it's some simple sinusoids that are summed, the in uh, constructive interference of some basic frequencies, sin different frequencies of some sinus functions. Okay. Um, so we have 4 channels basically, and we're displaying that. We can use a temporal filter here. Typically, we use a Butterworth filter that tries to, have the most flat frequency response. And it's kind of a, middle ground or a compromise, because Chebyshev maybe, sometimes needs more computational power. Yeah, and you use a band, we use a band pass here because we want frequencies between 8 and 12 to pass, which in our case is alpha waves. This is, intuitive. Band stop means that you will stop the frequencies between the two, and high pass means that you want to pass above 12. Low pass means you want to pass only the frequencies below 8, and so on. Okay, now then you can use, for example, a DSP allows us to do a lot of different operations on the signals. Here we can, just do a power of the signal, compute the power of the signal, which is typically used, for motor imagery. We use the signal power. And then we need to average the power of the signal because um, a very high sampling frequency. So when we do the power, it kind of the signal doesn't really make sense, and we need to average the signal. And then when we average the signal, we then do the inverse, and we basically, the inverse from an exponential function, we kind of normalize our function. That's something that we typically do in motor imagery. I want to talk about spatial filters here. So for example, usually we can have like 4 input channels. Okay, that means 4 electrodes, and we in the output we only want to see 1 channel, and here we basically averaged all of the 4 channels, meaning just 1 over 4. It's 0.25, 0.25. So each of the electrodes we basically used the average of all of them and sum them into 1 channel. I think there's another example here. Yeah, here we can use a spatial filter. We can use the bipolar spatial filter, which is also a fixed spatial filter, which basically means we um, subtract one electrode like C3, and then we use one electrode like C3, and then we subtract the neighboring one while leaving the other 2 um, intact. So the other 2 neighboring electrodes intact. If we wanted to subtract all 4 of them, we would use it would be the Laplacian filter. So we use, yeah, again, so in the output, so this is like we sum all of these values from these 4 electrodes, and then we output it into 1. We sum them into 1. So instead of using the spatial filter, we can also just use a channel selector where we can basically select, our first channel. This means selecting our first channel, or selecting a third channel, and so on, depending on how many channels we have, or from 1 to 5, select all of them, or reject you can reject from 1 to 4, from 1, sorry, to 5, and so on. So you can reject your channels. What you can use here also is univariate statistics, meaning that with this you can extract the mean, the variance, range, and so on. Some really useful information from your signal, and here from our channel 1. And also we can use, for example, again, a simple DSP to say, okay, if my mean here, because I chose the first, this is variance, this is range, and so on. So if I connect the mean here, so I can choose within my DSP, I can say, okay, if my signal is above, or if my signal mean is above 2, then I don't know, do something with that. It means that it's a peak, or I don't know. You can do whatever. Yeah, and you can notice here that you have 2 input, and you basically can do that if you right click here, and you can inputs. You have inputs here, and then you can add new, again, input C, and so on. So you can add inputs to. Not every box allows you to add inputs. You see here, so you cannot add another output, for example. So okay, so with the DSP you can add different channels, or you can put channel A or channel B. For example, here, yeah, this is what you can see here. So, in example, channel, we chose a channel 1 and channel 2. And here in the DSP, we want to see, I don't know, channel 1 minus channel 2, which we can again achieve with the spatial filter, basically putting 1 minus 2. It does the same thing, actually. So it's a two ways to do the same thing. And then, for example, yeah, let's see everything. So here we have the difference between the two channels. Yeah, and we're displaying it in only one as a one channel. So we have a difference between two neighboring channels. Then here we have the beta power. So we filtered the signal between 12 and 30 hertz. Then here we have the different spatial. I think we did the same thing. Wait, let me see. What was it? Yeah, we did the spatial filter difference, but using not using the channel selector, but only using the spatial filter, which is basically the same thing. Then yeah, we used alpha power. What else? Yeah, we also you can check out the alpha. And yeah, I mean you can check out a lot of different, you can play with the signal. It's basically what the generic stream, the generic oscillators, is used for, so that you can test it and do a lot of interesting processing and learn what different boxes are used for.